So, have you ever wondered why sitting in front of a fan cools you down so much faster than just sitting in still air? I mean, it seems like a pretty simple, everyday thing, right? But the answer actually lies in an invisible, microscopic layer of fluid that hugs every single object around us. That invisible blanket holds the absolute secrets to how heat moves, and understanding it is the key to mastering thermal management. Today, we're diving into this explainer to demystify the intense math behind fluid dynamics and thermal management. We'll be looking at the principles of convection and, most importantly, visualizing the boundary layer. We're going to take what usually looks like a massive wall of complex calculus and turn it into clear, physical mechanics that you can actually picture in your head. Okay, let's dive right into our roadmap for this explainer. 1. Viscous flow and friction. 2. Pipes and free streams. 3. Boundary layer mechanics. And finally, 4. The thermal boundary layer. Let's get to it. Starting off with part 1, viscous flow and friction. There's this quote from the source material that gives us a really perfect mental model. The physical mechanism of viscosity is one of momentum exchange. Imagine a fluid moving in perfectly smooth layers, what we call laminar flow. Instead of seeing a solid stream, picture microscopic molecules constantly hopping back and forth between these fluid layers. And as they hop, they're swapping momentum from the faster-moving layers over to the slower ones. That molecular momentum exchange, that's what actually creates the physical drag or viscous shear force on a surface. Now, what's really interesting here is how we can physically see this fluid behavior change as it moves along a flat plate. Right at the leading edge, the flow starts off as this perfectly smooth lamina. But as it travels further down the plate, bam! Small disturbances amplify, and suddenly the flow churns into these turbulent macroscopic chunks. It transitions from microscopic molecular hopping to just this massive chaotic swapping of fluid masses. So how do we predict exactly when that smooth flow is going to burst into chaotic turbulence? Engineers use the Reynolds number. You can think of this as the ultimate dimensionless speed limit of the fluid universe. It basically groups together the free stream velocity, the distance from the leading edge, and the fluid's kinematic viscosity. On a standard flat plate, that critical transition into turbulence usually happens when this ratio hits between 5 times 10 to the 5th and 10 to the 6th power. Let's actually contrast these two physical states. Laminar flow is smooth. It relies on that tiny microscopic molecular momentum exchange, giving us a really nice curved parabolic velocity profile. But turbulent flow, that operates through macroscopic churning chunks of fluid. Because these giant chunks are aggressively transporting so much momentum across the flow, they effectively flatten out the velocity profile, except for a tiny microscopic laminar sublayer that still fiercely hugs the surface. All right, moving right along to part 2, pipes and free streams. Now watch what happens when this flow enters a completely enclosed pipe. A boundary layer starts to grow right at the entrance, hugging the inner walls. But because the space is confined, well, these layers keep growing inwards until they meet in the center and completely fill the pipe. When this fully developed flow is laminar, you get a beautiful parabolic shape. But when it's turbulent, you get a much blunter, flatter profile right there in the core. Inside a tube, the rules actually change a little bit. That threshold for turbulence, it happens way sooner. When we calculate the Reynolds number using the pipe's diameter and the mass velocity of the fluid, we find a very specific threshold. Basically, any Reynolds number over 2300 inside a tube, and the flow is usually observed to become fully turbulent. But hey, what happens to the fluid that's way out there, far away from the pipe walls, or far out in the free stream away from our flat plate? Well, when you get far enough away from the surface, those velocity gradients basically drop to near zero. That means the viscous shear forces virtually disappear. We actually call this inviscid flow. By treating the fluid as totally frictionless, engineers can use the famous Bernoulli equation to easily balance the kinetic and potential energy of the flow. Now, it is definitely worth noting that if the fluid speeds up enough to actually compress, like air flowing at really high velocities, those simple frictionless equations just aren't quite enough anymore. We suddenly have to track internal thermal energy. You can see the exact ideal gas properties and specific heat constants for air right here. By using these, we can accurately calculate pressure drops and energy changes in compressible flows. Which brings us to part 3, boundary layer mechanics. Okay, calculating the exact math for every single microscopic molecule in a fluid is literally impossible. So to avoid that impossible math, engineers draw an imaginary box
which we call a control volume, around a tiny elemental piece of the boundary layer. By drawing this box, we can just simply balance the forces and momentum entering the box against the forces and momentum leaving it. It's like a giant puzzle. To turn these incredibly dense integral momentum equations into something we can actually, solve, we apply 4 crucial simplifying assumptions to our control volume. First, we assume the flow is steady and incompressible. Second, no pressure variations as you move vertically away from the plate. Third, constant viscosity. And fourth, we completely neglect viscous shear forces acting in the vertical y direction. When we apply those assumptions, we get the integral momentum equation. So the really crucial point here is understanding exactly what physical forces are fighting each other inside that box. Fundamentally, this equation just balances the viscous shear forces, the physical drag slowing the fluid down on the bottom face, against the pressure forces pushing the fluid forward. And by solving that delicate balance of forces, we arrive at this remarkably elegant equation for the thickness of the boundary layer, which we denote with the Greek letter delta. Let me tell you why this matters. This specific piece of math literally lets an engineer map out exactly how thick that invisible friction blanket is at any specific point on a moving object, like an airplane wing. It's a real game changer.
And finally, part 4, the thermal boundary layer.
Just as a physical wall drags on a fluid to create a velocity layer, a hot wall heats the fluid to create an identical, stacking temperature layer. The source material defines it perfectly. A thermal boundary layer may be defined as that region where temperature gradients are present in the flow.
Let's move on and see how this energy balance builds on that control volume box we talked about earlier. We have to track the thermal energy convected in, the heat transferred from the physical wall, the energy convected out, and any net viscous work done on the element. Though, quick aside, the heat generated by viscous friction is usually totally negligible unless your fluid velocities are extremely high.
So, how do we link our physical boundary layer to our thermal boundary layer? We use the Prandtl number. This thing is the ultimate translator in thermodynamics. It's the exact ratio of a fluid's kinematic viscosity to its thermal diffusivity. In simple terms, it tells you how effectively the physical momentum of the fluid maps directly onto the spread of temperature through that very same fluid.
And that brings us to the massive takeaway of this entire explainer. We literally had to do all of that complex fluid math because the momentum equations and the energy equations physically mirror each other. Knowing exactly how the fluid physically moves, drags, and churns is the only way to predict exactly how the heat will transfer into it. The velocity gradients strictly dictate the temperature gradients. We started this whole thing by asking why a fan cools you down. Well, it physically sweeps away that heated thermal boundary layer, forcing your body to constantly heat new, cooler air. So now that you have the mental tools to actually visualize these unseen physical momentum and thermal layers, I want to leave you with this. How might you change the physical shape of an object in the real world to perfectly manipulate the heat it releases? Keep that in mind next time you look at a heat sink or the curve of a car engine. Thanks for joining me on this explainer, and I'll catch you next time.